So this one is your non-linear reconciliation.
Oh, you mean 6.8? Yeah. 6.8.
Yes. Yes. So have you gone through it? Any doubt? Or yes. So why it is called nonlinear? Because here you can see that the terms is yes, of course, the obvious reason is the terms are nonlinear. So that is the reason. So here, if you see the first example, 6.8.1. So it is saying that they are actually using a recurrence relation to find the number of triangulations of an n-gon, right?
Mm-hmm.
Right. So just for a quick example, what does triangulation is? So for example, this if I have a fourgon, so this is a fourgon, right? So this I can triangle like this, or I can triangle it like this, right? So there
Mm-hmm.
are two ways. So a2 equals to 2. If an, if you denote the number of triangulations, number of different triangulations of a n plus 2 gon, so that is an. Fine.
Mm-hmm.
So the thing is, you have to prove that it follows the reconciliation. So it is a0 an minus 1 plus a1 an minus 2 and so on up to an minus 1 a0. So this is the reconciliation. We have to show that it satisfies this reconciliation, and then we have to solve for the general thing. Right.
Mm-hmm.
So a2 is 2, so that is first thing. So also next one is a3 that I am not drawing. You can check the drawing from the figure. So that is 5, because if you take the 5 gone, that they have given the 5 figures how to triangulate it.
Mm-hmm.
Right.
Mm-hmm. So, so I looked at the way they try to expand everything. The thing is, uh, if I understand it correctly, what they are trying to do is, um, they they want a because if I were to do this, I'd be thinking I can separate. So for example, knowing for example when n equals or rather a2. So there are four sides. It's
Yes.
yeah. So when it has four sides, they're this many. I'd try adding just one more vertex, but
Okay.
they're adding two vertices, or are they? They're adding two vertices, right? So on page 260, they said they form the n plus two god.
N plus 2. Yes, yes. N plus 2 gone, because an we are referring to number of triangulations of n plus 2 gone. Yes.
Say that again.
Yes, an, the recurrence term, that an, that is the number of triangulations of n plus 2 got. So that is the definition. So that's why that n plus 2 is coming.
Okay. Okay. Okay.
Yes, because it will start from 4 only, right? Because yes, we can start from 3, but that is only only triangle. So there is no triangulation actually. So I think they are starting from 4. The number of vertices or number of vertices of the polygon, they are starting from 4.
I see. I see.
Right. Yes, should I explain, or have you?
Uh, okay. Now, I'll try and I'll try to say what I think they are saying, but
Yes, yes.
if at
Well,
any point I got it wrong, correct me. So, uh, I think the next what they're trying to do is since they want to get the recurrence relation,
right.
uh, they they try to break it. Yes, so basically break it into uh smaller polygons. Let's say for example, they say choose an arbitrary side. I guess should you choose a vertex or just a side?
Yes. So actually, the side. Okay, let me draw. So the thing is, so now we are starting with a polygon that has n+2 vertices. So since I cannot draw, so I'll draw a circle. So we can just think it of a polygon with some sides. So suppose these are the vertices. So this is 1, 2, 3, and so on. And since it is n+2, so this is n+1 and n+2, and other vertices are like this. So now, yes, so we are particularly choosing a side, because now if I choose any vertex, suppose here, then if I join this one and this one, so this will be this will be a triangle, right?
Mm-hmm.
Yes. So that's why they are choosing a side.
I see. I see. I see.
Right. So the partition, what they are doing is, so what you told, that is correct. So we are trying to use the reconciliation. So we'll use the what we know about the smaller polygons, right? So that's why once we choose this, so this will break into two parts, right? The polygon. So now we can use the reconciliation, or the smaller things that we know that we can use. So that is the idea.
Okay. I guess
Hmm.
in this
Yes.
particular graph that you drew, if you connect one vertices one and n+2,
Yes.
uh, it doesn't divide because these two vertices are they are if you connect them,
Yes. Yes.
that doesn't divide the polygon
No. No.
into
No. No. That,
smaller.
that does not divide, because they are already adjacent, right? Because there are two consecutive vertices in a polygon, right? Because one is the starting vertex and n+2 is the last vertex. Means however you name it, right?
Uh-huh.
So they are
Hmm.
already adjacent. So that is not dividing actually. We'll choose a third point, because for a triangle we need 3 points, right? To triangulate we need 3 points, right? So we'll choose a third point. So this third point we can vary along the circle. So the thing is, so I can choose like this, or I can choose like this, any. So this third point I can vary along the other vertices from 2 up to
I see.
n+1.
I see. I see. I see. I see.
So
I
now
see.
after I choose this third vertex, now it gets partitioned into one part, and this is the second part.
Hmm. Okay, so this divide okay into two polygons. I guess we need to give it a name. The
Yes,
third the third vertex.
yes, yes. So this is R they are giving in the books. So 1 and 2
Okay,
are
so
adjacent, right?
R R. Okay, R. So there is a so one on one side you have a 1 2 R, so
Right.
that's an argon.
Yes, that we will say, that will see. But the thing
One
is,
two three four.
what will be the range of R? So R can vary from 2 to n+1, right?
Yes, yes.
So r can vary from 2 to n+1. And this triangle, so we can denote what they are using. So it is 1 comma n+2 comma r. So these are the three vertices that is creating the triangle, right?
Yes. And
Okay.
then the other, so yes, this is so on one side, on this graph it would be the right side. So 1 to
Yes.
uh it's still 1 to r, right? So
Yes. Yes.
vertices 1 to r. So
Yes.
so
Yes. So
yes,
this is
that's a polygon. That's a
right. Right.
polygon.
So PR.
The other
So this is PR.
yes, the other polygon, I guess it doesn't matter from which vertex to which vertex. It's how many vertices there are.
Yes. How many vertices
So
there are?
so there will be in there will be m plus 2 minus r vertices, right?
Yes. So what we actually do is, so n+2 minus r, then plus one, right?
Oh, it's off by what? Oh, okay. Okay. Yeah.
Right.
One,
So
two,
r and
three.
n+2 both are inclusive, right?
Oh, yes, 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 yes. Okay. You,
Right.
you know, this is I make this mistake a lot when coding. It's off by one. It's like
Yes.
off by one. Okay. So yes. So the other polygon has m plus two minus r plus one. That is m plus three minus r vertices.
Right. So it is P of this thing, right?
Uh. Okay. I guess now we start to try to use a recurrence relationship because within, let's say, PR and also P, within both polygons we can break it down into further, assuming we can break it down
Yes.
to.
So the smaller things we can assume. So the thing is corresponding to PR. The thing is a r minus 2, right? That is how we are defining, because an is the number of triangulations of n+2. So corresponding to
Mhm.
PR, it will be a r minus 2, and corresponding to this one, it will be a n minus r plus 1, right?
Oh, you mean that? Yes, yes, yes. They correspond to that. Yeah.
Right. So now what we can do is, so an is nothing but this is the summation r equals to 2 to n plus 1. So you can vary r from 2 to n plus 1. And the number of triangulations will be nothing but the product of the triangulations of this part and this part, right? Because for every triangulation here, I will get another triangulation here. So that's why the product, right?
Oh, this part I actually don't understand well. Can you say it again?
Yes, yes. The thing is, okay. So suppose I am fixing one r, right? Now I am fixing one r. Then I have
Hmm.
to find all possible triangulations, right? So this has a r minus 2 triangulations, right?
Yes.
And for each such triangulations, here there are a I n minus r plus 1 triangulations, right? So total number of triangulations will be product of them, right? The same thing, similar thing. So you have three ways to choose one object and five ways to choose another object. Total number of ways is 3 into 5, right? So that is what we are doing.
Oh. Okay, okay. Now I see. Now I see why. Now I see why. Now I see why.
Right, now you are varying r. So r summation, I think that is clear. R equals to 2 to n plus 1. And inside the summation, it will be a r minus 2 times a n minus r plus 1. Right.
Hmm.
So now we are just scaling the index of the summation. So just to make it look beautiful, it's like neat. So k equals to 0 to n minus 1. It is a k, a n minus k minus 1.
Hmm.
Right.
I see. I see. Yes, I think that's just a preparatory work because then they then go into generating function. Uh,
Right. So this is the reconciliation formation is fine. So now we have to solve the reconciliation, right?
yes. Uh, A0 is.
Yes. Tell.
Uh, how did they get to A0 is 1, I guess. That's
Yes, that will come. So the thing is, okay. So let us start the usual way. So we'll take ax, capital AX to be the generating function. So n equals to 0 to infinity n exponent. So this is the generating function corresponding to an, right? Okay. So now the thing is, it is starting from. Okay, so they are just separating out a0. So let us do like that. So ax minus a0. So it is summation n equals to 1 to infinity an xn. So they are separating it because we know an for n greater than equals to 1,
Mhm.
right?
Yes, I guess my question was that you see the initial conditions they only gave okay, okay. I know A1 is 1, A2 is 2, but they
Yes.
just gave A0 as 1. Okay.
No, yes, that will come. So yes, that will come.
And then okay, so that's a
So a0 is
uh,
1 because that is just vacuous, right? So a0 means the number of vertices is 2, right? So there is only one way. There is no way of triangulating, right? So there is one. That's why it is 1.
I see, I see, I see.
Right. So the thing is, we are just separating out a0 because I know the reconciliation for an, that is from n greater than equals to 1. So now we'll just substitute it here. So it will be double summation. So n equals to 1 to infinity. And now n is k equals to 0 to n minus 1. Expanded. Yes. Then after that, how they are doing?
Uh, t- to be honest, whenever I see double summation, I usually my brain freezes. Sorry.
Yes. So yes. So at least we can write some terms of the summation. Then it will be clear. So okay. So for equals to so suppose n equals to 1. Then the inside bracket has only one term, right? Because k equals to 0 and n minus 1 is also 0. So it will only go one term. So that is a0 and x, right? Then
Wait a second. So if it's 1,
yes. So if n equals
n
to
is
1,
1,
this is 0.
so there's only 0. Okay, so that's A0, 1 minus 0. Oh, okay, 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 okay. Yes, yes, yes.
Yes. So that is the first term. So now tell me when n equals to 2, what happens?
Then we need to go from, then we have K0 and K1.
Right.
If K is 0, then it's A0 times A1.
Right.
But if it's K2,
One.
K1, then it's A1, A0.
Right. This is x square. Let us do one more term, then we'll get an idea. So what about k n equals to 3?
3, that's K0, K1, K2. K0 is A0, A1. 2
Right.
plus k1, that's a1 a1,
Right.
and then a2 a2.
A0. Yes. So like that it will go on. So yes. So the number of the coefficients in the corresponding to the exponent or power of x, that is the same number, right? So x square has two coefficients, x cube and three coefficients, and so on, right? So the thing is, we can able to find the actual value. Yes, if we can represent somehow this expansion in terms of ax, right? So if we can do in terms of ax, then it will be good, right? So at least what you can
Sorry, you mean x or ax?
ax because we want to find a formula for ax, right? Because we want to find a formula for ax, right? Then only we can compare the coefficient and find the. That
I
is how
see, I
we
see,
use the generating function, right?
I see,
So
I see.
what I want to do is, so if I can express this whole thing in terms some function of ax, some function of ax, then I can use the usual technique, right? To isolate of ax and then find out the formula, right? So that is the usual technique,
I see, I see.
right? So yes, at least one thing that is obvious that x we can take out common, right? Because everything has x, so we can take out x common. So yes, so then we are left with a0 k0 plus x square and so on. Yes, now we have to figure out. Okay, so now I know ax. I know so ax is a0 plus a1x and so on. The thing is, from seeing this term a0. So okay, just to make it clear. So let us write a0 also in the expanded form and so on. Right. So the thing is, here if you just observe our ax, so here you can see that a0 is there, and if I one more ax is there, and if I multiply just both of them, then a0 is 0 will come, and for x what I will get I'll get cross multiply, right? So I will have
Hmm.
so let me just copy. So if I multiply these two things together, so then what I'll have is this a1 I'll cross multiply with a0 I'll cross multiply with a1, and that will be both coefficient of x. So that also matches. So similarly for x square, I'll do this one with this one with this one, and this middle two ones. So that's why it is also matching, right? So it is nothing but ax square,
Wow. Oh, oh, okay, 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 okay.
right? So yes, so this one just by observation you can see that this is nothing but ax whole square. So yes, so now it is just simplified into one line. The what is the expression? So I have ax minus a0. It is nothing but x times ax square, right? So now we can just substitute the value of a0. A0 is 1. So I actually got a quadratic equation, right? In terms of ax.
I see. I guess one question. So, in this case, even as we have this infinite series,
Right.
we kind of, so I guess it is easier to tell. But what if it is more complicated?
More complicated, like
So I mean, for example, here you can tell, okay, so this is A0, A1, and the A1, A0, and then they're basically repeating itself. So naturally, it can cause you to suspect, okay, maybe it's something time multiplying itself in some way.
Right.
So that's what I mean by, okay, this is maybe more obvious, especially if you are highly trained in math.
Yes.
But what if it's not so obvious? Are there other ways you can, I guess, get a so like you're guaranteed that there's a method in most cases to I guess to unpack or factor the
Uh, yes, yes. I understood your question. Yes, yes. I don't think there is a generalized method that you can follow for anything. So I think that only comes by experience, by solving the problems. I think that is only the thing. The thing is, the only basic idea what we have is, so I have to express this whole thing in some terms of x. Then only I can get a formula for x, right? So, so that is the reason. That is the reason you have to try and see that which thing works. So usually polynomial or exponential, mostly around these things it will work. So for example, here it is ax square, so it is just a polynomial in ax. So yes, most of the things works around these ideas.
I see, I see, I see, I see, I see. Okay, okay. So they I guess we can just write the what the book has
Yes, yes.
on this.
So from here directly you can use that quadratic formula and we can have the ax. So ax is nothing but 1 plus minus root over. Yes, 2x. Yes, after that, what you're doing. So we got a formula for x. Now you have to find the coefficient of x power n. So that is our main aim, right? Yes. So now how to do it?
Uh, I I guess just to confirm, this X is just there for counting. It's not the well, we're not supposed to plug numbers into it, right?
X.
Because this X comes from the generating function
Yes, yes.
earlier,
X
so
comes from that generating function. Yes, yes.
I'd assume the X here you're not supposed to plug numbers into
No,
it.
no, no.
It's just
So yes, yes. So here x is just a variable. So we are not plugging numbers.
okay, okay.
Yes. So now you have to find the coefficient of x power n from this. So yes, so we can easily that use that binomial thing, right? So the fractional thing we can use. So the for the part of 1 minus 4x to the power half. So for this I know usually the what is the coefficient of x power n, right? So there is nothing but half chosen times minus 4 to the power n, right?
Uh, co- coefficient of
So I think this we covered, right? So this is the generalized binomial thing, right? So I think we covered that negative binomial and then fraction binomial. This is the
oh, yes, yes, yes. Yes, we did.
so actually this does not have any combinatorial significance, but we can extend the definition from that combinatorial term that n choose r to these higher things, the fractional and the negative one, right? I mean, just as a formula we can extend. Means there is no real life significance, but yes.
Okay. Okay, remind me how do you expand if it's not even an integer?
Yes, yes. So that is the thing. So here we don't think about it as an integer or that thing. Just we are using the formula. So the thing is, n choose r. Our formula was n factorial divided by r factorial into n minus r factorial, right?
Yes.
Yes. So the thing is, okay, we are using n in the denominator, but anyway, then we have to use something else. Otherwise, it is confusing. So let us use opposite r chosen because we are here using n in the denominator. So r minus n factorial, yes. So the thing is, so this I can express as r times r minus 1,
Oh, oh, okay, okay, okay. I no, no, I see. No, I see. No, I see.
right? So
No,
r
I see.
minus n minus 1 plus 1, right? So this is the thing. So up divided by n factorial, right? So choose n. So this part is always integer. So this part is defined. But now this part is just an algebraic quantity. So it does not contain anything factorial thing. So this is algebraic quantity. So I can replace r by anything. I can replace r by fraction. I can replace r by negative quantity. Anything.
Gotcha, gotcha.
Right.
Okay.
So I think that is what they are using. So yes. So the simplification is just simple simplification. And once we simplify, then we are returning back to our usual binomial coefficient because the factorial thing is coming again. Right?
Uh,
So should I explain the that process what they're doing? Or?
I think the expansion is mostly fine. It's just that how should I say it? So like they took they took 1/2 from the top of the from the enumerator
Right.
from the numerator, sorry, numerator, from the numerator of the fraction,
Okay.
uh and also -1,
All right.
and also they plug that to the so 1/2, they plug that to the denominator. Okay, okay, mostly fine. I guess uh 2 over n-1, 2 over.
So the numerator does not have all the terms, right? So that is one observation we have to do, right?
Sorry.
The numerator does not have all the terms, means we cannot directly now replace by factorial, right? So that's why you have to adjust, right?
Wait, sorry. Does it have or does it not
Uh,
have?
it does not have all the terms. It is only having the odd terms, right? After just simplifying the first step, that is what I'm saying.
Oh
When
yes,
I
yes, yes,
take
yes.
out,
Yes, that's true.
when I take out the half, so it does not contain all the terms, such that I can directly write factorial. So that is what I'm saying. Yeah, so we adjust up and down by multiplying the even terms. So then we'll get 2n minus 2 factorial, and the denominator will have n factorial, and the extra terms are 2, 4, 6, and so on, up to 2n minus 2, right?
Yes, I know, I know, I know. I guess the rest of it looks fine to me, except from the second last to the last. Can you remind me of which what they are doing?
Yes, yes.
So
So the second last step, let us write. So second last step is this one. So n minus 2 factorial and n minus 1 factorial times n minus factorial. So up to this is fine, right?
up to this, yes.
Yes, yes. So now it is nothing, right? So it is just the usual binomial coefficient, right? So if you take this is the n thing, capital N, suppose. So n choose r, suppose we are doing. So then it is r is your n minus 1 and capital N is 2n minus 2. So then it is just that formula, right? So let me write down, then it will be clear. So 2n minus 2 choose n minus 1. So that is the usual formula, right?
So n is 2n minus 2. R is n minus. Oh, 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 oh. Oh, okay, 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 okay.
Right. So they I think just wrote it in bracket. That's why 2 times n minus 1 they just wrote.
Oh, okay, okay. Oh, oh, I see, I see, I see, I see, I see.
Right.
Uh, I see. Yes, up to this. This is
Yeah, so this is the coefficient of x power n in this part, 1 minus 4x to the power half. So now we have to adjust because here I have a division by x also. So actually, this is not the coefficient of x power n in the original thing because that will shift. One shifting will occur. So I think that we can do it next. So what I have is, so x is 1 by 2x that I just now did. So then summation of n equals to 1 to infinity 2 by n. So that minus thing we are taking. Plus minus is there, right? So we are taking the minus thing. So that's why this minus is gone. 2n minus 2. Choose n minus 1. Power x n, right?
wait. So I think they we wrote earlier there are two possibilities,
Yes,
right?
it's plus
Because
minus, right?
so why did we settle for the minus?
Yes, it's because an is the counting thing, right? So we are counting. So an is a counting object, right? So it gives us a count of some type of objects, right? So it cannot be negative, right? So that's why we are taking the negative one and neglecting the positive one because here already I am getting a negative sign. To adjust it,
Uh, okay. So uh because is it because the is it because 1 minus 4x to x and coefficient of x and is it because the coefficient of xn, the one we just did,
yes,
has a
negative sign.
and therefore in since we know we have a positive one, the only choice we have is to choose the negative one, so the negative sign can cancel out
Yes,
the.
yes, that is the reason. Yes,
Oh, okay, okay, okay.
yes, because eventually this the coefficients of x power n, that is a n. So that is a counting thing, right? So that cannot be negative. So yes, that's why we reject that positive thing and take the negative one only.
I see. Um, so the entire reason why we did the or maybe not the entire reason, but I guess the reason why we're motivated to find the coefficient of xn in 1 minus 4x square root is that because we need to find out whether or not it has a positive or negative sign?
No, no. The thing is, the only if you look into the formula of Ax, what we got. So the thing is, these parts are settled, right? So this is there is nothing to do in these parts. So only this will have a Taylor series expansion, right? So anyway, I had to find the Taylor series expansion of this part, right? Because from that only I will get the x power n and the coefficient of x power n.
Okay. Oh, I see. I see. Oh, okay. So because neither 1/2x or nor one will be able to generate to be a source where you get a0
Yes, yes, that is the
okay.
implementation.
Okay. I see. I see. I see. Okay. Um. So now we're back to h. Okay.
Yes, so this is what we got. So now you have to shift that shifting thing that you have to done, that you have to do. So this 1 by 2x now can go inside. So it is now n equals to 1 to infinity. The 2 will gets cancelled. So 1 by n, 2n minus 2, n minus 1, and x power n minus 1. Right. So this we can shift the whole thing. So from n equals to yes, yes. So the shifting can be done, right? So just 1 minute. So it will be 1 by n plus 1. I am just shifting n by n plus 1. So it will be 2n. Choose n, and it will be x power n. So the index will be from, tell me, what will be the shifting of index? 0
Wait,
to infinity.
sorry. Actually, one second, one second. So we moved. So we canceled out two with two.
Right.
And okay, we canceled x with x power n. Okay. Uh, this gives us this. Oh, so shift. Okay. I didn't see the index. Okay.
Yes.
That's
So
how. That's how. Okay.
yes. So we're just shifting it. So now that is the coefficient, but we want a n. So a n is 1 by n plus 1, 2n chosen. So yes. So this is a well-known quantity. That is what is called the Catalan numbers. So this is the number of ways that we can triangulate that regular polygon. So an is the number of ways of triangulating p of n plus 2. So n plus 2 vertices are there. So this is the number of ways.
I see.
So I think yes, right?
Yes, this one's fine. This one's fine.